Alright, welcome back. We're now in the third part, Arrhenius theory and Ostwalds dilution law. By outline, we look at Arrhenius theory, Ostwalds dilution law, some illustrations, and we conclude. Now, Arrhenius studied the conduction of current through water solutions of electrolyte. He found out that the conductivity of solutions are due to the presence of ions. Now, Arrhenius theory of ionization may be stated as follows. When dissolved in water, neutral electrolyte molecules are split into two types of charged particles. These particles are called ions, and the process is called ionization. The positively charged particles are called cations, and those having negative charge called anions. The theory assumes that the ions are already present in the solid electrolyte, and these are held together by electrostatic force. Now, when they are placed in water, these neutral molecules dissociate into the anions and cations. Look at it. We have an old view and a modern view. And that's what this means. These are the ions in solution. So we call this the theory of dissociation of ions. Now, secondly, there will be an equilibrium between the undissociated molecules and the ions, which is this. And if you apply the law of mass action, the equilibrium constant will be given this. Here we call that now the dissociation constant K. These and these are the products, so the concentration of the product divided by the concentration of the reactant, which is the electrolyte. 3. The charged ions are free to move through the solution to oppositely charged electrodes, which is of course what we said. So this movement of ions contributes to electric current, and this explains the conductivity of electrolytes, which of course gives the phenomenon of electrolysis. 4. The electrical conductivity of the electrolyte solution now depends on the number of ions present in solution. Therefore, the degree of dissociation of the electrolyte determines whether that electrolyte is a strong electrolyte or a weak electrolyte. Now we look at Ostwalds dilution law. From the Arrhenius law of dissociation, we have that the degree of dissociation alpha is equal to lambda, that's our molar conductivity, divided by the molar conductivity at infinite dilution. And this holds for weak electrolytes, where the ionic interaction effect is minimal. Arrhenius law of dissociation was quantitatively treated by Ostwalds in his dilution law. And this law establishes the relationship between the degree of dissociation and of course the dissociation constant of a weak acid. So let's use a 1:1 electrolyte. We mean 1:1 here is 1 mole of positive ion and 1 mole of negative ion. You can also have something like A2B, which makes this 2:1, or AB2, which makes this 1:2. For instance, sodium chloride is 1:1, calcium chloride is 1:2. When we apply that same law of mass action, we have the dissociation constant to be that. So we look at the concentrations, look at it, n into 1 minus alpha, because it's 1:1, this is n alpha and n alpha. So when we put the concentrations here, we solve and get this. And then we vote the relationship between concentration and volume, and we'll see the variation of the degree of dissociation with the dissociation constant. If we move further, since alpha, which is from Arrhenius law of dissociation, we have that alpha is equal to this. So we substitute for alpha, and we have that the dissociation constant Ka is equal to this. And we can solve this equation to arrive at this. So I want you to take your pen and paper. Take your pen and paper and see if you can simplify or break down this equation 3.23 and see if you can arrive at equation 3.24. And if you look at that, it means that we can plot a graph of 1/lambda against concentration, and then we'll get our intercepts, which of course we can from there calculate the molar conductivity at infinite dilution. So it is from this equation that we got those graphs we had in the last section, where molar conductivity for strong electrolytes can be extrapolated, but for weak electrolytes cannot be extrapolated. So these are simple illustrations. We're given some values, conductance, and the rest. We're told to calculate the equilibrium constant for acetic acid. Go through this. If there's any problem, you ask your questions. Another example, the dissociation constant of N-butyric acid is given, molar conductivity at infinite dilution is given, and then we're told to calculate the specific conductivity. And of course, we follow all the equations we have seen, Ka, we're able to calculate value of alpha, then we find the molar conductivity, and then we can get the specific conductivity. Thank you very much. We've come to the end of this module. We have looked at Arrhenius theory of ionization or dissociation, Ostwalds dilution law, and looked at some illustrations. Thank you very much. See you in the next class.